Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button. Homework for Lecture 103. Problem number 1. Show that the charge density of the smaller sphere is higher than the larger one, assuming their electric potential is the same. Okay, fairly straightforward. So number 1, so we draw a little picture. We have a sphere of radius, I guess we're calling it little r, and it'll be connected with a wire to a larger sphere of radius big R. So, and we're assuming that because of the wire connecting them, that the potential is the same at both spheres. Well, this implies that the charge on little sphere divided by R is equal to the charge on the big sphere divided by big R, which in turn means that the ratio of Q, the charge on the little sphere over the charge on the big sphere, is equal to the ratio of their radii, little r over big R, which means that the charge on the little sphere is equal to the ratio little r over big R times the charge on the big sphere. Okay, so now we're just going to rewrite this. I'm going to replace this term here, Q sub r and Q sub big R, with charge densities, which means that I have to basically multiply everything times their volume. So we'll have so this is a surface density. So we just need the surface area of a sphere. So we'll do 4 pi r squared times q r over 4 pi r squared. See, these cancel each other out, but I'm going to replace this with sigma sub r here. And this will be equal to the ratio little r over big R of q big R divided by 4 pi big R squared times 4 pi big R squared. And this will have the 4 pi's will cancel on both sides, and we'll have r squared, and then I'll divide this r squared over here like so. And so you can see that what this is going to do is going to swap this ratio, and we'll get big R over little r times sigma big R. So the charge density on the small sphere is larger than the charge density on the big sphere because r is greater than little r. I mean, this is greater than 1, so the charge density is bigger than the charge density of the large sphere. All right, problem number 2. Find the number of electrons stored on a parallel plate capacitor in which the potential between plates is 12 volts. And so I have a little diagram of this capacitor. Let me just draw it here. So this is for number 2. It's a hard diagram to draw, but so we have a plate in front. And what is its dimensions here? This will be 0.1 meters in this direction and 0.1 meters in this direction. And it's separated from another plate, which I'm going to draw over here, if I can, like this. So we see these are different plates. There we go. The spacing between them is 1 millimeter. Okay, so that's 0.001 meters. Okay, and what else do we have here? We're putting, this will be the positive plate, and we're putting 12 volts on that, which means the negative plate will have 0 volts on it. Okay, I think we have all the information that we need. Let's see here. So the capacitance is going to be equal to epsilon naught A divided by D, the separation distance between them. And that's going to be, well, what's the epsilon naught we'll have here, times the area, which is going to be 0.01 meters squared, because 0.1 times 0.1 is 0.01. And I'm just going to, instead of writing epsilon naught on top, I'm going to write 4 pi k on the bottom, because I don't remember off the top of my head what epsilon naught is equal to. So the D is 0.001 meters, and then I'll have to multiply this times 4 pi times 9. Oh, that's right. It's epsilon naught is 1 over 36 pi times 10 to the 9th. Times 10 to the 9th. And if we work this out, let's see what we have. We're going to get powers of 10. We'll get, and I'm going to scratch this epsilon naught out here because I didn't use that. I put it all down here as k. Because remember, k is equal to 1 over 4 pi epsilon naught. So I inserted all that in here. So that's powers of 10 will be 10 to the minus 2 plus 3, and then the minus 9, and then we'll get this over 36 pi. 9 times 4, 36 pi. I think I said 27 pi before. That was wrong. 36 pi. And that, let me just punch it into the calculator. Okay, that's 8.84 times 10 to the minus 11 farads. I think I ran off the room. So the capacitance is then going to just be 88 micro. No, not micro. Whoops, that's bad. 88 picofarads. Very small. And what else do we need here? Let's see. I completely forgot what we were doing. Find the number, the number of electrons stored. So now I have the capacitance. Okay. So Q, the charge, is equal to the capacitance times the potential. Well, we know the potential is 12 volts. So we're going to get 88 times 10 to the minus 12 farads times 12 volts. And that is going to equal 1.1, right? 1.1 times 10 to the minus 9 coulomb, so it's about a nanocoulomb. Now the number of electrons is just going to be equal to this charge, 1.1 times 10 to the minus 9 coulombs, divided by the amount of charge of a single electron, which is 1.6 times 10 to the minus 19 coulombs, and that is equal to, that's 6.6 times 10 to the 9 electrons. So about 6, or rounded up to 7 billion electrons. A lot of electrons, but not really. Okay, here's a fun problem. Number 3. Calculate the capacitance of the Earth, assuming a radius of 6.371 times 10 to the 6 meters. And then part B, we'll calculate the electric potential energy of the Earth with a net charge of minus 8 times 10 to the 5 coulombs. Hint, treat the Earth as an isolated spherical capacitor. And then part C, we'll ask what is the electric potential of the Earth in volts, presumably. So let's see. I believe this number of coulombs for the Earth is roughly that given by Mr. Faraday himself in the 19th century, though I probably rounded it to a more convenient number. So number 3, so we're going to treat the Earth as an isolated spherical capacitor. Now a more accurate representation of this would be a regular spherical capacitor with the ionosphere acting as like the upper kind of surface of the capacitor and the Earth's surface acting as the lower surface. That'd be a little more detailed, and it's kind of unclear exactly. There's not like one number for the distance to the ionosphere, so it could be a little bit complicated. But we'll just treat it like an isolated spherical conductor, which means that the second surface is out at infinity. And so the capacitance is just given by C equals 4 pi epsilon naught times r, the radius of the Earth in this case. So part A, C, is going to be equal to big R over K, which is just equal to 6.371 times 10 to the 6 meters divided by 9 times 10 to the 9th. Well, the units of Coulomb, I think it's Newton meter squared per Coulomb squared. And this will be equal to, and I just took advantage of the fact that 4 pi epsilon naught is just equal to 1 over K. Divide this out, what do we get? We get 0.708 times 10 to the minus 3. So that's about 7.1 times 10 to the minus 4 farads. Okay, I don't know how I feel about that number, but I guess it works. Part B, we're now going to calculate the potential energy. So U, potential energy, will be equal to Q squared divided by 2 times the capacitance. Okay, so we'll use the number for Q that we were given. We were given that Q was equal to 8 times 10 to the 8? No, 10 to the 5. 10 to the 5 coulombs. So 8 times 10 to the 5 coulombs divided by 2 times 7.1 times 10 to the minus 4 farads. So this gives us, oh, I got to square this. Whoops. So this needs to be squared. Whoops. All right. Square that. That's going to give us what? Turns this into 64 times 10 to the 10 divided by 2 times 7.1, so that's going to be 14.2 times 10 to the minus 4. And in the end, punch that in, what do we get? We get 4.5 times 10 to the 14th joules. So that is a lot of energy. That's crazy, huh? Man. All right, and then part C. What is the electric potential of the Earth? Assuming that we calculate 0 to be at, say, ground level, we would get V is equal to Q over C. So just divide these two. That'll be minus 8 times 10 to the 5 coulombs. The charges stored on the ground are negative charges. That's what lightning does. About 100 strikes per second deposits all of this charge on the surface of the Earth throughout the course of a day. Of course, it varies a little bit from time to time, but divide by the capacitance that we found earlier, 7.1 times 10 to the minus 4 farads, and that gives us minus 1 times 10 to the 9 volts. So it's about a billion volts. That is quite a bit, huh? Quite a bit, and that's approximate. Just rounding stuff for convenience here. Okay, Earth is a capacitor. Right, number 4, a 6 microfarad capacitor is connected in series with a 12 microfarad capacitor, and the combination is connected in parallel with a 10 microfarad capacitor. What is the effective capacitance of the combination? Okay, problems like this, we definitely want to draw a diagram right out the gate. So let's draw basically a circuit diagram for this. So here we've got a 6 microfarad capacitor, and it's in series with a 12 microfarad capacitor. And this is in parallel with a 10 microfarad capacitor. Okay, so if I call this like arm 1 and call this arm 2, we want to figure out what the effective capacitance is in arm 1. That's 2 capacitors in series. Okay, and so we'll have 1 over C, and we'll call it arm 1, is equal to 1 over 6 microfarads plus 1 over 12 microfarads. And that is equal to, it's like 2 over 12 plus 1 over 12. equals 3 over 12, which reduces to 1 over 4. So C arm 1 is equal to 4 microfarads. And then we want to combine arm 1 and arm 2. The capacitance to give us the total effective capacitance through the circuit will be equal to the 10 microfarads plus the 4 microfarads to give us 14 microfarads. Okay, and our final problem, number 5. A 5 microfarad capacitor is connected in series with a 15 microfarad capacitor, and the combination is connected in parallel with a 12 microfarad capacitor. Across the two is at, the potential across the two is at 12 volts. What is the effective capacitance? How much charge is stored on each capacitor? And what is the total stored energy in the capacitors? Okay, let's take this piecemeal. First thing we want to do is draw a diagram again. Draw it a little differently this time. 5. I'll have my 12 volt arm up here. I'll have my 5 microfarad capacitor here and the 15 microfarad capacitor here. And then in this arm we'll have the 12 microfarad capacitor. Here's the 0 volts. Okay, so let's get the combination first, the 5 and 15 microfarad capacitors. So 1 over C is going to be 1 over 5 plus 1 over 15, and that's going to be 3 over 15 plus 1 over 15 equals 4 over 15. So C is equal to 15 over 4. So it's almost a capacitance of 4 microfarads. Now let's get the effective capacitance for the whole circuit. We get that's equal to 12 microfarads plus 15 over 4 microfarads. And that would be equal to, so it's going to be 48 plus 15 over 4 microfarads. And that is 63 fourths, which is equal to 15.75 microfarads. So part A, C effective equals 15.75 microfarads. That's the effective capacitance. Part B asked us how much charge is stored on each capacitor. Okay, so B, how much charge is on each capacitor? Well, charge, the relationship between charge and capacitance is given by this. So let's write down that the C5 and C15 will have the same charge on them. And so that's going to be 15 over 4 times 12 volts. I meant to say that this is, yeah, I kind of botched that up. Q is equal to 15 over 4 times 12 volts, which equals 4.5 times 10 to the minus 5 coulombs. And then for the capacitor C12, the charge is equal to, there's 12 times 10 to the minus 6 farads times 12 volts equals 1.44 times 10 to the minus 4 coulombs of charge. Good. And then part C asked, what is the total stored energy in the capacitors? Well, the potential energy is equal to 1/2 Q squared over C, which is also equal to 1/2 CV squared, which is going to be equal to 1/2. We'll use the effective capacitance of 15.75 microfarads times the 12 volts squared, and that is equal to 1.1 millijoules.